Hi, this is Hirono from 347 at JPL. I'm going to present UAS-based active hurricane sensing with information-theoretic path spanning. This was funded by FY20 HBCU MSI Program, and this is a collaboration with Professor John Park at North Carolina A&T University. Okay, so tracking and prediction of tropical cyclones are critical for adequate preparation and evacuation of lives and properties. Of course, I posted two pictures on the right. Do you know which hurricane this is? Anyone? It's Harvey in 2017, which hit Texas. Probably some of you remember. It's one of the worst hurricanes in history, and that's the hurricane that we used for simulation in this task. And hurricanes are interesting scientifically. It's difficult to predict. Why? There are two reasons. First, it develops on the ocean where there is not many weather stations, and second, it is a highly dynamic and localized phenomena. So, even after the landfall, the ground meteorological network is not dense enough to fully capture the phenomena. You often miss the sweet spots of it, and of course, satellites cannot directly measure the key parameters like precipitation, wind speed, and pressure. And also, for JPL, the understanding of hurricanes on Earth has some relevance to atmospheric science of gas and ice giants. So, how to better understand hurricanes, how to better predict it? The natural idea is to fly drones in the sweet spots when interesting things are happening. And of course, we are not the first to have that idea. NASA Armstrong, for example, they then tried them. They did this airborne tropical tropopause experiment from 2011 to 14. They flew Global Hawk above the hurricanes. And of course, the scientists, their desire is to fly through hurricanes. So NOAA is doing this Hurricane Hunter program, which they fly P3 above hurricanes and drop Coyote UAS. It's highly successful, but it's basically drop drop probes. So the airplane's control is pretty much limited to recovery after dropping. And of course, there is a growing interest in academia and also NOAA, I believe, on having more advanced autonomy on board, more intelligent path planning to fly in a more informative and safer way, and perhaps over a longer range or duration. So basically, we wanna build the strategic strength in this area at JPL. I think we are well positioned in terms of the technical assets that we already have. So the stated goal of this task was to develop a path planning approach for a multi-drone team to actively observe meteorological parameters in a hurricane. And to be honest, we haven't achieved this multi-vehicle part. We ended up with a single vehicle path planning due to the lack of time. The funding just 50K is pretty limited in time and resource, but the work that we've done can be directly leveraged to do path planning for multi-vehicles. Okay, so here is our high-level approach, which we will detail in later slides. So there are two components involved. The first is a meteorological simulation from JPL and a path planner from NCAT. And there are three steps involved here. The first, we spinned the numeric meteorological simulation to reproduce the hurricane observations from which we can create cost maps And second, using that cost maps, we ran the path planner, which is created by NCAT, and to come up with the drawn path. And finally, we ran the meteorological simulation again with the simulated observations from the airplane, drones, to evaluate the impact on the how much improvement we can get by adding the drones. This slide is about the model. The model was developed by the former JPL postdoc Masashi, who is now assistant professor at the University of Tokyo. He created this model called. It's based on. It's called PSU WRF ensemble Kalman filter model. It's based on commonly used WRF and CRTM models. It runs an ensemble of 60 simulations to represent the uncertainty of the phenomena and observations. And it has hierarchical structure in terms of spatial resolution. It first runs at the 27-kilometer resolution, and then 9, and finally 3-kilometer resolution. So all results that we have is based on the 3-kilometer resolution data. We used Hurricane Harvey as our data set, and we have conventional observations, which includes the ground-based observations, marine surface, radio only, and whatever. And but the uniqueness of this model, this particular model, is that it assimilates the brightness and temperature data from Gold-16 satellite, which improves the model accuracy substantially. The graphics on the right, that on the left, this is the real observations from Gold-16, and on the right, this is the reconstructed observations from the simulation, which agrees very well. Okay, so how we made the cost maps. So there are two cost maps that we created. One is the ensemble spread, which represents the uncertainty in forecast, and the other is the estimated forecast improvement. Basically, the sensitivity from observation to forecast. And here's the simulation timeline, and at one point in time where we make a path plan, we branch off another ensemble and run the sim towards the future. Actually, it goes ahead of time to predict the uncertainty ensemble spread and the sensitivity that we would have at the point of time when we fly the drones. And that's how we create those cost maps for path planning. And here are the examples resulting cost maps. One on the left is the ensemble spread representing the uncertainty, and on the right is sensitivity. And the main takeaway here, those are similar but different. Meaning that the location that has the greatest uncertainty in forecast does not necessarily be the place, the sweet spot that has the highest sensitivity to forecast. So that's why we used both maps for planning a path. And okay, so then I will talk about the path planning. Our path planner is based on RRT star. It's a sampling-based variant, commonly used variant of RRT. So on the chart on the right, it represents how it goes. It builds a tree first. It considers the directional constraint that requires the path to be mostly aligned with the wind direction, to be feasible and safe. So as you can see, the tree that represents the feasible and optimal path um, mostly aligned with the wind direction. And after you build the tree, you specify the goal location. Then you can pull out the optimal path from start to the goal. And we ran the path planner with three cost functions. One is what we noted MDM, minimum distance. And the other two use the cost maps from the meteorological models. One is based on the ensemble spread. So basically, flying where the prediction is most uncertain. The last one is maximum unstable sensitivity. That's basically fly so that we visit the places that has most sensitive to observations. Okay, and so here are examples, example results. Those are the ensemble spread maximization. ABC are maximizing the ensemble spread of pressure, temperature, and wind speed respectively, and D that combines all the three cost functions by it's basically linear combinations of the through some weights. And so this slide it's a bit complicated, but it's actually the most important slide, I believe. It's about how to integrate these hypothetical drone observations into the our meteorological simulation framework. Okay, so there is one simulation thread. It's not ensemble. We called the nature run. This is basically the ground truth. And in reality, it is not visible to humans. Only God knows, you know. So this is a ground truth, and out of it, we create the simulated observations, basically adding noise from this ground truth, and from which we run an ensemble forecast, which we do in reality. You know, we take observations and run the ensemble common filter. As I said, when we run the path planning, we branch off the ensemble, another ensemble, to create the cost maps that goes ahead of time. And we allow 3 hours between that point of time. We branch off the this another ensemble and the time that we inject the drone observations. This represents the time that we need to make the path planning and fly drones, command the drones to go there, etc, etc. And so this cost map goes to the path planner, and we make the simulated observations. The simulated drone observations again is pulled out of the nature RAM and added noise on top of it. That goes back to this main ensemble and run the ensemble Kalman filter to update the observation. And in this way, we can we can evaluate quantitatively how much impact this drone observation created. Okay, so here's the simulation results in a spatial view. So this label alphabet is wrong, but this is the ground truth, the nature run, basically God view. This middle, top middle, this is the prior. So this is before we inject the simulated drone observation. And the top right, this is the error before the drone. And the three bottom charts, these are the posterior, the errors after we fly drones and injected the simulated observations from drone into EKF. And note that the scale bar is different. Sorry about that. But the takeaway, by adding drone observations, it allows to better capture the vortex structure of the hurricanes. So main takeaway, by flying drones, yes, it gets better, of course. So what's the comparison between those three models? So this is the temporal view, or with regard to two metrics. One is the minimum sea level pressure. The other is the maximum wind speed at 10 meter in altitude. And here is the RMSE, the root square mean error of these metrics. This black line with plus labels, this is from the ground truth. The blue line, this is from the simulation without drawn observations. Another three lines that are the errors with drawn observations with distance spread and sensitivity costs respectively. So again, errors, the predictions with drones that agrees much better with the ground truth compared to the run without drones. That's for sure. So which of the three are is the winner? That's not obvious. We only run one simulation per each case, which is of course not statistically significant. It takes a day or two to spin this simulation. It's a huge numeric model. That's the limitation. So it doesn't tell the statistically significant result. But having said that, what we expected is the run with path band with sensitivity going to be the clear winner. It's not. There could be many reasons. Of course, the one is that we only run once, but also with the path banner is already sharp. It has a guaranteed convergence if you run substantially long time. But obviously we cut off before the convergence. Again, it's due to the computation resource, and so if we run longer in already sharp, maybe we can do better. So perhaps we should switch to the future work slide. But also we can arbitrarily choose the start and end locations. Oh, my daughter is crying for some reasons. Anyways, so where was I? Yeah, so optimizing the job start and goal locations. Maybe we don't have to set a goal. That's another thing. And also, as for the meteorological simulation, as I said, it's an improvement in the simulation optimization. Maybe using some supercomputing cluster to run statistically significant number of simulations. That's going to be important. And also scientifically, for this one, we focused on the early stage of hurricane development called genesis stage, but we are interested in doing the experiments on the different stages of the hurricane development. Okay, so that's all. And finally, I want to say, this work was supported by a great team. It was a collaboration with NCAT, led by Professor John Park, and the PhD student Justice Darko. He's the one who did the heavy lifting on path planning, with a guidance from a senior student, Larkin Folsom, who actually spent 2 summers at JPL. On the JPL side, it's me, Hui, and Masashi, who did the heavy lifting on meteorological simulation. He was a former postdoc at 329, and he actually accepted the faculty position at the University of Tokyo during this task. But he is also continued to be a JPL affiliate, and he continued the collaboration as a Nobel collaborator with us. Okay, thank you very much.